Okay, you all welcome to the finite element analysis lecture. The last class we discussed how to model the bar assembly using the finite element analysis. Today we are going to discuss how to model the two-dimensional trusses using the finite element analysis and to find the stress developed in each and every element using the finite element method. Okay, let's continue today's lecture. Okay. Today we are going to discuss about the two-dimensional trusses, how it model with the finite element analysis method. Okay, I think you already know what is meant by the two-dimensional trusses in your mechanics module. You may learn this kind of trusses. For example, this is the truss structure, the uniform cross-section bar, the connected using the pins or the trusses. The loads are acting at this pinned point. Okay, loads are acting on the pins. So then all the forces develop along these bars. Okay, then these bars are subjected to a tension or compression. Okay, according to the load applied. So then when taking the truss structure, all the forces are acting along these members. Okay, in axial direction. Okay, there's no lateral forces acting on the, if you take the one certain beam element, there's no lateral forces. All the forces are acting in axial direction of the that is the property of the truss structure. That is the way of designing the truss structure. Okay, then in this lecture we are going to discuss how to model these two-dimensional trusses and how to solve this kind of truss structure problem using the finite element analysis method. Okay, then let me take this example truss in here. According to the natural position of the truss structure, we have to assign the global coordinate system. Okay, if we take this kind of truss structure, what is the suitable global coordinate directions? These are the suitable, according to the natural position of the truss structure, these are the suitable global coordinate directions. Okay, I will draw it and very clearly. Let's take this the global coordinate system. By looking at the entire structure, we have to assign this global coordinate system. Okay, so normally as a rule we can say on the global coordinate system it should represent its natural position. Okay, it should represent its natural position. Okay, let me draw the truss structure. Okay, let's take something like this kind of a truss structure. Okay, let's take this kind of a truss structure. Okay, then let's take these points. Let's take these points as the x and the global coordinate x and the y directions. Let's take these elements as element 1, element 2, element 3, element 4, element 5, element 6, element 7. Similarly, we can mark the nodal points also. The node 1, and node 2, node 3, node 4, node 5. Okay, like that we can mark the nodal points also. Then the global forces acting on this each and every node. The global forces acting on each and every node we can mark in this kind of manner. Global force, we are using the capital letters for the when marking the global forces. F F1x. F1x mean we are resolving the global forces acting on the node 1 into two components in a two perpendicular directions called x direction and the y direction. Okay, then a resolve component in x direction we can mark it as the F1x. For the in a y direction, F1y. The global forces acting on the node 1 we are representing by the two forces as two perpendicular forces as x direction and the y direction component. Okay, similarly in here we can mark nodal force acting on this node 2 in x direction F2x, in a y direction F2y, like that. Okay, same as we can mark for node 3, node 4 and node 5. Okay, then F3x, F3y. Okay, like that. So then the nodal displacements also we can mark on this diagram, representing the two perpendicular directions. Okay, here d1x in this direction, d1y. Okay, that means the displacement of node 1 in a global, according to global coordinate directions, it may displace something on a two-dimensional plane. The resolve component in x direction is the d1x, resolve component in y direction d1y. Similarly, we can mark for node 2 d2x in a y direction d2y. Similarly, we can mark for the node 3 d3x d3y. Okay, for the according to the global coordinate system, we can mark all the forces acting on this global structure and the nodal displacement of the global structure in this kind of manner. Okay, I think you all got a more clear idea about that one. Then when you are going to obtain the element equations, thing is we have to assign the local coordinate system. Okay, let's see how to assign the local coordinate system. Okay, when we are going to obtain the element equations for each and every element, we have to assign the local coordinates according to the orientation of the each and every element. Okay, this one is called the global coordinate system. Okay, this one is called the global coordinate system. Then we have when we are going to obtain the element equation for each and every element, we have to assign the local coordinate system according to the orientation of the each and every bar element. Okay, let me assign the local coordinate system according to the element 1. Okay, let's see. Then this is the global coordinate system. X and the y. Let me draw the element. Okay, I am considering the first bar. So then I am going to assign the local coordinate system considering the first bar. So this is my local coordinate system. Okay, along the axis of the bar element, I am going to use the x hat. In a transverse direction, I am going to use the y hat. Okay, this is the local coordinate system. X hat, y hat is called the local coordinate system. X and y is called the global coordinate system. The global coordinate system assigned according to the for the entire trusses structure. Then the local coordinate system assigned according to the orientation of the each and every element separately. Okay, so this is the local coordinate system for first element. But if we take the third element, that may different from this coordinate system. Okay, if we take the third element, for example, if we take the third element, this orientation is this kind of, see? So then let's take the another coordinate system, another local coordinate system, x bar, y bar. Okay, these are the local coordinate system for x bar, y bar is the local coordinate system for the third element. Okay, these are local coordinate system for the first element. Okay, according to this local coordinate system, I am going to mark the displacements and the local forces. Okay, local displacements. Node 1. Along the x direction, the displacement. Along the x direction, displacement of node 1, d1 x. Okay, along the y hat direction, displacement of node 1, let's take it as d1 y hat. Okay, d1 y hat. Same as in here, along the x hat direction, the displacement of node 2, d2 x hat, along the y direction, d2 y hat. Okay, d2 y hat. Similarly, we can mark the local forces as also. Along the x hat direction, the local force acting on the node 1, element 1, f1 x hat, f1 x hat. For the f2 x hat. Okay, then what can you say about the local force acting on the node 1 in a transverse direction, in the y hat direction? Actually, in a trusses structure, all the forces acting on the members are acting along the axial direction. Okay, there's no lateral forces. Okay, so that means in a lateral direction the force is equal to 0. So anyhow we can mark that force in this kind of manner. In this direction, the local force acting on the node 1, f1 y hat, that should equal to 0, because in a trusses structure all the forces are acting along the beam, acting on along the element. So there's no lateral force. This one should be equal to 0. Same as in here, the anyhow we can mark this one, f2 y hat, that one also equal to 0. Okay, in this way we can mark the local forces and the local displacement according to the local coordinate system. Okay, then according to this marked displacement and the local forces, we can write the element equation for the element 1. For example, if we write the element 1 equation, okay, based on the local coordinate system, I am going to write the equation. You already know how to write this equation. f1 x hat, f2 x hat. These are the forces acting on the bar element. Then let's take the bar cross-sectional area E, the bar material elastic modulus E, the length of the bar L. Okay, 1 minus 1 minus 1 1. Then what are the displacement? d1 x hat, d2 x hat. Okay, these are the displacement. Okay, then these are the nodal forces, but in here you can see the f1 y hat and f2 y hat should equal to 0. Should equal to 0 because this is the trusses structure. In a trusses structure, all the forces are acting along the bar element. So those are equal to 0. Anyhow, I am going to include these forces in this equation. So let's see how to include that. Those are in this equation. This is the equation we obtained for the element 1 equation. Then I am going to include these. These are also f1 x hat, f1 y hat, f2 x hat, f2 y hat. AE divided by A. d1 x hat, d1 y hat, d2 x hat, d2 y hat. Okay. Then the d1 y hat and d2 y hat are non-zero values because this point can displace on a two-dimensional position, two-dimensional plane. Okay. Then the these are non-zero values, but these are should equal to 0. So when writing the equation, this entire row should equal to 0. This entire row belongs to this f1 y hat should equal to 0. That means the 4 elements equal to 0. Here also f2 y hat, the entire row should equal to 0 because when multiplying this one should equal to 0. So then we can insert these values in this equation. So 1 0 minus 1 0 minus 1 0 1 0. Okay, similar equation we just only include f1 y hat and f2 y hat. Well, I will mark this equation as equation A, capital A. It is a very important equation. The element 1 equation according to the assigned local coordinate system. Okay, element 1 equation according to the assigned local coordinate system. I think up to now everything clear, no? Okay. Okay, then similarly we can obtain this local equation, that means the local element equation according to the assigned local coordinate systems. Okay, for each and every element according to the assigned local coordinate system, we can obtain this kind of equations. Okay, here we are having the 1 2 3 4 5 6 7 elements. We are having the 7 equations. Okay, here the 7 elements. Then we are having the 7 equations. All of these equations are in different coordinate systems. Okay, different coordinate systems, but in here some are coinciding each other. So for when modeling the 2 6 and 4, we can take the global coordinate system, but for others they are having the different coordinate systems. Okay, that means simply we can say the all of these in a truss structure, all the elements are in different coordinate systems. Okay, then in a finite element modeling, what we are doing, we are obtaining the element equations. For each and every element. Then we are going to assemble all of these equations to obtain the global solution. But in this situation, all of these equations are in different coordinate systems. Okay, then we can't assemble with these different orientation of coordinate systems. So then we have to transform all of these equations to a one particular certain coordinate frame. Okay, so then that coordinate frame we are taken as the global coordinate frame. All of these local element equations we are transformed into a global coordinate direction. Then we are having the 7 element equations with reference to the global coordinate system. Then we can assemble all of these equations to obtain the global solution. Okay, that is the thing we are going to do. So let's see. Let me explain that further. That one. Here we obtain element equation with reference to the local coordinate system. Okay, then what we want is, okay, let me draw the element 1 again. The global coordinate system with the element 1. Okay, then element 1 f1x, the nodal force acting on the node 1 for element 1 in a global coordinate direction f1x. In this direction f1y, in this direction f2x, here f2y. Okay, then in this time these are not non-zero values. That means the f1y not acting in a lateral direction, a perpendicular direction to the element, so it's a non-zero value. In this time. So then in this direction, the displacement d1x In this direction, displacement d1 y. In this direction, displacement of the node 2 d2x. In this direction, node displacement of the node 2 d2y. Okay. Then here we mark the local forces and the nodal displacement nodal displacement according to the global coordinate system. So then we want the element equation in this kind of format. Okay, that means f1x, f1y, f2x, f2y. Okay, then the global stiffness, element stiffness matrix with reference to the global coordinate system. So then the nodal displacement with reference to the nodal displacement vector with reference to the global coordinate system. Okay, we want this kind of equations. Okay, we want this kind of equation. If we are having this kind of equation for all of these elements, then we can easily assemble all of these equations, because all of these equations are in same coordinate frame. So then we can assemble all of these equations to obtain the global solution. But if these element equations are in different coordinate systems, we can't assemble. Okay, that means we want this kind of format. Okay, then next step, I'm going to transform this equation to a global coordinate system. Okay, I'm going to use the coordinate transformation equations to transform this one. I think in your mathematics you may learn the coordinate transformation. If not, I am explaining it now. Okay, let's see how to transform this equation in a different coordinate system using the coordinate transformation equations. Well, let me explain this coordinate transformation. Okay, let me explain this coordinate transformation. Well, this is the global coordinate system I will draw. This is y, this is x, the global coordinate system. Let me draw the local coordinate system also. Let's take this is the local coordinate system we assign according to the orientation of the element. Okay, let's take the x hat in a perpendicular direction. The y hat. Okay. Then let's take our, this is O, coordinate 0. Then let's take, this is the O dash point. This point is represented. Let's take this point is represented in this node 1. This O dash point is representing node 1. Okay, let's take the O dash point is representing the node 1. So then let's take, when applying the forces, when the truss structure is loading, okay, when the truss structure is loading, let's take this point as is displacing to this kind of point. Okay, let's take this kind of position. Okay, let's take. Okay, then I will mark that point. It may displace to a this kind of position. Okay, let's take. This kind of position. Okay, then according to the local coordinate system, the displacement we can mark. According to the local coordinate system, the displacement we can mark. So what are this displacement? According to the local coordinate system, this displacement is called let's take this point as yeah, A. Then this displacement O dash A is equal d1 exact. Okay, let's take this point as the B. The O dash, the B is equal d1 y hat according to the local coordinate system. So then similarly we can mark it on a global coordinate system. After displacing the point somewhere in this kind of position, initially it was in this kind of position. So then this displacement, this value is equal d1x according to the global coordinate direction, the displacement in x direction. Okay, displacement in y direction we can mark in this kind of manner. This displacement, this one is equal d1y. Okay, d1y. Okay, I think this diagram is clear to you. The O dash A is equal d1 exact. That means this is a node 1. After it loading, it has displaced. It can displace to a two-dimensional plane. Let's take this kind of position. It has displaced. Let's take this point as C. Yeah, let's take this point as C. Then another important parameter we have to mark, this one. To the horizontal, let's take this element is forming the theta angle in anti-clockwise direction. That means this angle is equal to, okay, this angle is equal to theta. Okay, let's do some geometric constructions. Geometric construction. I'm going to extend this CA line. CA line. Okay. Then again I'm going to draw a perpendicular line. Let's take this point from this point to this line. Okay, so perpendicular. Let's take this point as A, B, C. Let's take this point as D. Then from this point I'm going to draw another perpendicular line. Let's take this point as A, B, C, D, E. Okay. Okay. Then this angle is a 90 degree. Is a yeah. This one is equal 90 minus theta. Here it is theta. Here it is theta. Is a 90 minus theta. Here is 90. Here is theta. Okay. Okay. Then we can write this equation. O dash A is equal O dash D plus dA. Okay, then what is this, that value? O dash A is equal O dash D means this value is equal from this triangle d1x cos theta. d1x cos theta plus dA. dA is equal to here this length A B C D E. Let's take this one as F. This point dA is equal to FE. dA is equal to FE. From this equation, CFE equation, d1y sin theta is equal to FE. So d1y sin theta O dash A. What is O dash A? O dash A is equal d1 exact is equal d1x. For the cos theta, I am going to use the letter Z. The d1y I am going to, for the sin theta I am going to use the S. Okay, let's take this equation 1. Okay, equation 1. Then AC, sorry, yeah, AC is equal from this triangle EC minus AE. Okay, AC is equal, you can see, sorry, AC is equal O dash B. O dash B is equal CE. What is CE? CE from this triangle CFE triangle, this height is equal d1y cos theta, minus AE. What is AE? This AE is equal to DF. AE is equal to DF from this triangle DO dash F triangle, d1x sin theta. What is O dash B? O dash B is equal to d1y hat, d1y C minus d1x S. Let's take this equation as equation 2. Okay, then we can put equation 1 and equation 2 in a matrix form. Equation 1 and equation 2 in a matrix form like this. d1 x hat, d1 y hat is equal to CS minus SC d1x d1y. Okay, this is a transformation equation. This is called transformation matrix, coordinate transformation matrix. Okay, in using this coordinate transformation matrix, we can transform. You can see then this one has transformed to a local. In a other way, we can transform the local to a global. But then we can include. Okay, this is the equation we obtained for the element 1. Node 1. Similarly, we can obtain this kind of equation for the node 2. I will write that equation directly. For the considering the node 2. Okay, sorry. I will first of all I will write the obtained equation d1 x hat, d1 y hat, CS minus SC d1x d1y. This is the transformation equation for the node 1. By following the same procedure, we can obtain the transformation equation for the node 2 also. Then we are getting this equation. I will directly write that equation 2y hat is equal CS minus SC, the d2x d2y. Okay, these two equations we can obtain using the considering the geometry of this kind of figure. Okay, so then I'm going to put these two matrices in a one single matrix. Then we obtain by combining these two matrices matrix equations in a single equation, the d1 x hat, d1 y hat, d2 x hat, d2 y hat is equal d1x, d1y, d2x, d2y. Okay, and here we are getting the c s0 0 minus s c 0 0 0 0 cs 0 0 minus sc. Okay, by combining these two equations we are getting this kind of equation. Similarly, this is for the nodal displacements. This is for the nodal displacement. Similarly, by following the same method, we can obtain the force transformation equation. Similarly, I will write that equation: f1 x hat, f1 y hat, f2 x hat, f2 y hat. By following the same method, that means by representing these force vectors to a scale on this kind of a diagram, we can obtain this equation also, same by following the same procedure. Okay, I am not going to do that one in here. 0 0 cs 0 0 minus sc. Sorry, f1x, f1y, f2x, f2y. Here we are having the nodal displacement transformation matrix and the nodal force transformation matrix. Okay, so then in the first equation, that means earlier we marked this equation A. Okay, equation A. Okay, instead of this vector, okay, instead of this vector, I am going to put the multiplication of these two. Okay, multiplication of these two. Instead of this vector in equation A, instead of this vector, I am going to put these two. Okay, these two. Okay, let's see how to rearrange this equation A by inserting these vectors. Okay, I will directly write that equation. Okay, the equation A. Okay, these two cs0 0 0 0 minus sc. F1, sorry, yeah, f1x, f1y, f2x, f2y. So then in here, AE divided by L, AE divided by L. Then I'm going to use this one. 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0. Then instead of this one, I'm going to multiplication of these two. That means cs0 0 minus sc 0 0 0 0 cs 0 0 minus sc. Okay, so then the d1x, d1y, d2x, d2y. Okay, finally we are having this equation. This means the equation A we have rearranged by inserting these multiplications in this equation. Finally we are having this equation. Okay, then I am going to simplify this equation. That means we want to make this matrix into subject. Okay, we want to make this matrix into subject. How to make this matrix into subject? We have to remove this one. How to remove this one? How to remove this one? By multiplying the inverse of this matrix, we can remove this matrix. Okay, by multiplying the both side, I am going to multiply the inverse of this matrix. So then you may know matrix operations. So I am not going to teach the matrix operation in here. So I think you all know this one. You know, by multiplying the matrix with the inverse of that same matrix, form the identity matrix. Okay, identity matrix, and multiplying the identity matrix with the matrix form the same matrix. So I will direct write that equation multiplying the inverse of this matrix. Okay, then in the left hand side we are remaining f1x, f1y, f2x, f2y. The both side we have to multiply with the inverse of this matrix. Okay, AE divided by L. So then inverse of this matrix in the right hand side also we have to multiply with the inverse of this matrix. Inverse of this matrix. CS00 minus SC00 00 CS 00 minus SC, inverse of this matrix. So then other matrices 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0. Okay, CS 00 minus SC 00 00 CS 0 0 minus SC. Then the d1x, d1y, d2x, d2y. Now you can see we are having the element equation with reference to the global coordinate system. Okay, global coordinate system. Here the global coordinates, then this equation is called the multiplication of these three matrices. We are having the 4x4 matrix called element stiffness matrix with reference to the global coordinate system. Okay, multiplication of all of these three matrices and this term called element stiffness matrix with reference to the global coordinate system. Let's see how the multiplication of this one. First of all, how to take the inverse of this matrix. You can see it's a orthogonal matrix. In an orthogonal matrix, is a property. The inverse is equal to the transpose of this matrix. Okay, that property we are going to use to take the inverse of this matrix. Okay, this is the orthogonal matrix. In an orthogonal matrix, its inverse is equal to the transpose of the matrix. So instead of the inverse, we can take the transpose of the matrix. Okay, I will write that by taking the transpose of that matrix. Okay, then I will write that K by including the transpose of this matrix, because this is the orthogonal matrix, the inverse is equal to transpose. That means in this matrix, if this is matrix is a T, its inverse is equal to its transpose for orthogonal matrices. So I am going to use the transpose. that matrix. So then element stiffness matrix with reference to the local coordinate system, that is equal to AE divided by L into matrix, the transpose of this matrix C S 0 0 minus S C 0 0, then 0 0 C minus S, yeah, sorry, yes, no, sorry, plus, then 0 0 minus SC is the transpose of that matrix. So then other matrices are same, 1 0 minus 1 0 0 0 0 0 minus 1 0 1 0 0 0 0 0, the C S 0 0 minus S C 0 0 0 0 CS 0 0 minus S C. Okay, then this is the element stiffness matrix with reference to global coordinate system. So I am going to multiply these matrices. First we want to multiply these two, so then the resulting matrix we have to multiply with this one. So then how to multiply this one? Let's take AE divided by L, the multiplication of these two matrices, the minus C and the 0, the second one is 0 minus S 0, then the third one minus C the 0, then yeah, C 0, then for this one yeah, plus, no, minus S 0 S 0. So then this equation, the C S 0 0 minus S C 0 0 0 0 CS 0 0 minus SC. Then we have to multiply these two also. So then the K matrix is equal multiplication of these two, here multiplication of C square then here the CS here we are having minus C square, then here we are having minus CS. Okay, then for this one, to multiply with this one, we are having the CS S square minus SC minus S square minus C square minus SC C square CS minus SC S minus S square CS here S square, sorry, here the AE divided by L. This is the the local either stiffness matrix, the element stiffness matrix with reference to the global coordinate system. So then we can write the element equation. Then we can write the element equation with reference to the global coordinate system. If you know the element stiffness matrix, we can write the equation. The f1x, f1y, f2x, f2y. We are going to relate with the stiffness matrix AE divided by L. AE divided by L. Our equation C square CS minus C square minus CS SC square minus SC minus SC square minus C square minus SC C square CS minus SC minus SC square CS SC square. Then the d1x, d1y, d2x, d2y. This is the element equation. This is the element one equation with reference to the global coordinate system. Okay. Then if for each and every element in this equation, for each and every element we have to obtain this kind of equation. That means then we can assemble all of these equations, because all of these equations are in one coordinate frame called global coordinate frame. So then we can, all of these equations we can assemble to form the global equation. Okay. Then when we are going to obtain the equations for each and every element, you can directly use this equation. You can directly this equation. The C mean in here, C mean the cos theta, the S mean sin theta, the C square mean cos square theta, S square mean sin square theta. Here what is mean by theta? Theta if angle of inclination of the element by element with reference to the x coordinate system. The angle is measured anti-clockwise to the x coordinate, positive x coordinate direction, the theta. Okay. So then for each and every element, by substituting this theta value, by using this equation, we can obtain this element stiffness matrices for each and every element. Then we can, all of these equations we can assemble. Okay. This is how we are then after obtaining the global equation by substituting the boundary conditions and the known forces, known displacement and the known forces, we can find the unknowns. This is how we are solving the this kind of two-dimensional truss problem using the finite element analysis method. Okay. Then let's see how to calculate the stresses. How to calculate the stresses, stress developed in each and every bar element in this method. Okay. The next theory part is the computation of stress for a bar in two-dimensional trusses. Okay. Let's see how to compute the stress developed in a truss bar element on a truss, two-dimensional truss. Okay, let's take a certain bar element. Okay, I'll draw the certain bar element. This is the local coordinate system, exact. Okay, then the displacement of the let's take this node 1, node 2. The displacement of the node 1 d1 x hat, here the d2 x hat. Okay, the displacement of force, nodal force f1 x hat, nodal force acting on the node 2 f2 x hat. That means the nodal force acting on the node element on this element f2 x hat, nodal force acting on the node 1 on this element f1 x hat. Okay. Then for this bar element, we can write the element equation. What is the element equation? For the bar, for this bar element, we can write the element equation: F1 x hat, F2 x hat, AE divided by L. 1 minus 1 minus 1 1 D1 x hat, D2 x hat. Okay, without including the F2 y hat 10 because in a F1 y hat and F2 y hat are 0, so I will not include that one in this equation. Okay, then I'm going to separate. Okay, I'm going to separate this element on this kind of, I'm going to section this element in this kind of position. So then I will draw that separated element. Okay, then I'm going to mark all the forces acting on it. So what is this force? F2 x hat force is acting in this direction. So along this direction, what is the force is acting? Let's take this cross section as A. If the cross section as A, let's take the developed stress in this situation, let's take it as a sigma. So then what is the force? The force is equal A into sigma. A into sigma. Okay, force is equal to A into sigma. So then these two should be equal. Okay, consider the equilibrium of this separated beam part. We can write the equation. F2 x hat is equal to A into sigma. A into sigma. Then from this equation, what is F2 x hat? From the equation F2 x hat is equal to AE divided by L. F2 x hat. That one is equal to minus 1, 1 D1 x hat, D2 x hat. Okay, from the equation. So then from considering the equilibrium, we have obtained this equation. Let's take this equation 1, equation 2. From equation 1 and 2, we can obtain by equating these two in the right hand sides. We are obtaining this equation. A sigma is equal minus 1 1, sorry, AE divided by L, no? Yeah, sorry. A sigma is equal AE divided by L minus 1 1, the D1 x hat, D2 x hat. Okay, then we can cut this one. For the sigma, we are having the equation. Okay, for the sigma, we are having the equation. E divided by L minus 1 1 D1 x hat, D2 x hat. Okay, this equation we can use to calculate the stress developed in each and every bar element, each and every truss member. If you know the local displacement, we can directly use this equation to find the stresses. But if we don't know the local displacement, we have to use the transformation equation to find that one. Okay, we have to use the transformation equation to find that one. So what is the transformation equation? Earlier we obtained for this transformation. Okay, this is a transformation equation. So then if we don't know this local displacement, we can use this equation to find the stresses. Okay, I will insert that one in this equation. Okay, In this equation, we want d1 exact and d2 exact. Here, sorry, d1 exact, d1 exact and d2 exact. The multiplication of this term with this one, and the multiplication of this one with these matrices. Okay, I am going to write the reduced equation for this one by taking these only these two rows and this column. Okay, then I can write that equation. The sigma is equal E divided by L minus 1 1. Okay, so the d1 exact, d2 exact, the equation. If we don't know the local displacement, we can use this equation, minus 1 1. The transformation matrix CS 0 0, only for these two I am writing 0 0 CS d1x d1y d2x d2y. Then we can use this equation when we are calculating the stresses on a two-dimensional trusses. Okay, I think you all got a more clear idea how to solve the two-dimensional truss problem and to find the stresses developed in each and every member using the finite element analysis method.